Okay, let's make a start. I have a few challenges. I have an echo. Apologies. Our first speaker is Ojas Parekh from Sandia National Labs, and he's online.
Hi, everyone. Good morning. Can you all see my screen?
Yes, we can see your screen.
All right, fantastic. Sorry, what was that, Jaren?
And we can hear you as well.
Okay, great. Should I go ahead and get started?
Yes, please do.
Okay. So the first thing I want to do is I want to thank the workshop organizing and report writing team for our quantum computing and networking BRN. Sorry, just a sec. Okay, good. Hey, hopefully you can see me too now. And especially my co-chair, Pavel Lugovsky, who works for Amazon and kind of did all of this on sweat equity. Right? And so I'm just going to jump in and tell you the main grand challenge we identified. And, I wish it were really provocative or surprising or, would generate a lot of discussion, but it's probably pretty much what you expected. We want an end-to-end quantum advantage. There should be some rigor involved. And ideally, we want to identify some utility or problem of practical value that we're addressing. I mean, this is basically what everyone wants. So, this was not at all a surprise, but maybe the way in which we approached it, might be a little different than others. So let's dive into that. And so what we did was we kind of thought of computing, as sort of standard as a stack. And we actually have many kinds of stacks because we're also looking at computing and networking. So, and even, in computing, there are different kinds of stacks depending on what you're focusing on. So this is our general stack, and then I'll give an example of a specialized stack later on. And then we identified 5 priority research directions, kind of targeting each layer of the stack. And so I want to, the ultimate goal is to explain those to you. But before I do that, I want to set up some context. So, obviously finding quantum advantages, discovering quantum utility is challenging. I mean, we've kind of been stumped for a while. We have some promising leads, but this is still a big challenge. And so why is this, and what things should we be worried about, and what things, should we find encouraging? So first, let me tell you about, just an example of a stack that's kind of focused more on advantages. So for this stack, we're kind of sweeping all the hardware and architectures at sort of a bottom layer, but we want synergy. So we want the system that we design, either through some co-design effort or some synergy and design of algorithms, closely working together with hardware designers. We want hardware that's able to realize any algorithmic advantages we come up with. And, even algorithmic advantages, there's sort of many components, right? So you need the algorithms, you need kind of novel algorithms, but you need, decent, precise, accurate resource estimation and performance assessment. You need applications, and then you need everything that puts the bow on it. You sort of need to package everything together and demonstrate that there's some kind of advantage. So now let's talk about algorithms a little bit. So, the word algorithm, actually, it's pretty loaded, right? I mean, it could be anything from a textbook algorithm to some highly optimized implementation running on, specialized hardware. And so we've got everything from the blue sky at the top to, the crisp earth at the bottom. And hopefully, we start at the top and we understand that there are some advantages to be had. And, there's some rigor around that, and then we can work our way towards the bottom. And maybe sort of a grassy layer in the middle helps, where we're kind of designing abstract models, but have kind of physically inspired features. So the point is, in all of these layers, your goals and your approach are a little bit different, and they can actually be vastly different. So what we'd really want to do is just say, hey, you know, we're at the bottom, we have quantum computers, let's just run stuff and let's just see, you know, what kind of advantages we're getting. And if it's for a problem we care about, you know, let's call it a win and move on, right? And this is kind of what we do classically. You know, we just solve things and either we're happy or we're not. And maybe as problems go harder or more complex, you know, the story changes, but then we also adapt accordingly. Now, you know, one thing here is a big question is, are we going to see advantages for near term or current term quantum computing? And this is kind of a big worry, you know, I mean, is this really going to happen? I mean, for me, I'm actually worried that we will see advantages on near or current term quantum computers, you know, and why is that? Well, the reason is that if I give you kind of an empirical demonstration of some kind of advantage, then, you know, what you're really seeing is it's telling you a story about, hey, I tried a bunch of classical methods, I tried the state of the art, and I'm seeing that on this problem or on these instances that I care about, you know, I'm getting some kind of quantum advantage. Or even if it's not an advantage, I'm seeing some promising scaling and, you know, that's indicating some kind of crossover. Okay, I mean, that's great. But what that's hiding is that, you know, there was an opportunity cost. So we're investing in quantum computing, but really, you know, if that advantage isn't based on some quantum mechanical feature, I mean, the first thing to say is I actually really expect that we will see lots of advantages of that kind, you know, empirical demonstrations, kind of suggesting some kind of advantage on current and near-term quantum computers. And I mean, the reason for that is these are amazing pieces of hardware. I mean, they're probably doing something right, and there's probably some kind of problem where you're going to see, you know, desirable behavior. You're going to see something exciting happening. But if those advantages aren't based on raw, you know, some raw feature that quantum mechanics provides, then I mean, there was this opportunity cost where you could have just built something classical. You know, maybe we could have invested more in software or research, or, you know, there was some hardware we could have built, or there was some modification we could have made to existing hardware, and we could have solved the problem a lot more efficiently or cost effectively, or, you know, whatever you care about. And so that really brings us to the main point, which is, you know, did we really use quantum mechanics in coming up with quantum advantages? Now, you know, if we actually had quantum computers and they were ubiquitous, of course we would take any kind of win, you know, they give us, right? We just solve the problem in the most cost-effective way, and if that's on a quantum computer, great. But since we're still in kind of the early stages, you know, this opportunity cost matters. And by the way, please feel free. I've left plenty of time for discussion, so please feel free to jump in with any questions or comments. Okay, so right, so there are two questions here. You know, why do we care if we have advantages based on quantum mechanics? And I kind of addressed that. And the second is, are there any examples? You know, is this something that's even like sound? You know, is this something we can actually hope for? So I'm going to give you a recent story that kind of demonstrates the second point there. Okay, so, you know, normally we think of, or we might think of quantum advantage or quantum utility as kind of a needle in a haystack problem, right? You have, you know, you're looking for a novel quantum algorithm, and they're really, really hard to construct. And we only have, you know, we have lots of quantum algorithms, but there are only a handful of basic techniques that kind of empower them. So, I mean, this in itself is kind of challenging, but like what really happens is you just sort of get more hay dumped on you. You know, I mean, you know, if you're focusing on quantum algorithms, I mean, you may miss the point that you had to actually pick a problem where it was possible to get some kind of significant quantum advantage in the first place. And by the way, you know, you'll see in these slides that there's some maybe implicit assumption that exponential, or at least like super polynomial quantum advantages are the things that we should be aiming for. And what I really mean by that is we just want quantum advantages that are going to be kind of large enough or asymptotically large enough that, you know, they'll put us over the overhead for fault tolerance or any other kind of overhead, right? So we need the advantages to be significant enough that they kind of pay for whatever extra cost, you know, is required to do quantum computing. And then, okay, even if you found a problem and you found a nice algorithm for it, I mean, you sort of need the evidence that there was no efficient classical algorithm, you know, that overnight someone's not going to kind of make that advantage evaporate. And then finally, even if all of those things go right, I mean, you've actually got to turn this into a utility story. You know, you've got to find some application where this is actually making a difference. And so, any one of these things would be challenging, but we've got to make sure all of them happen. And so this is one of the reasons why quantum advantages, or at least sound quantum advantages, are really difficult. And, so with quantum advantages, normally we're just thinking about making things go faster, which is great. But if we look at what's going on with that, quantum speedups are actually kind of limited. I mean, even if you look at Shor's algorithm for factoring, we have an exponential speedup, but it's only against the best known classical algorithm. I mean, granted, there's a lot of evidence that, maybe there isn't a substantially better classical algorithm, but it's still possible, like I was saying on the previous slide, that, essentially overnight, someone could come up with a better classical algorithm and make that advantage go away. So ideally, what we really want we want exponential advantages against the best possible classical algorithm. And that seems like a tall order. I mean, how do you do that? How do you do that without knowing what the best possible classical algorithm is? But surprisingly, this is actually possible. And what kind of empowers this is if we look at resources beyond running time. So, other things that really matter, we've learned even classically for HPC and stuff, are things like communication, things like energy consumption, things like memory. So, if we consider some of these other resources, we can actually get the kinds of advantages we want. And so the idea here is maybe we have to be a little more creative about where we look for quantum advantages. So, okay, another story is that, I said earlier, we really want these quantum advantages that are based on quantum mechanics, but there's kind of a disparity here because, we also want quantum advantages for like the problems we're already solving. And these are somehow, unless you're looking at problems in quantum simulation or something like that, these are classical problems. And so, at least maybe at a high level, you would think that if quantum mechanics is giving you some advantage, then, maybe your problem should have something to do with quantum mechanics or quantum physics. Like, why should quantum mechanics help you on linear algebra, right? I mean, okay, maybe you were lucky and maybe that happens, but how do you explain that? And so it actually turns out there is a nice explanation. So the explanation goes as follows. So normally, when we think of solving problems conventionally, you just have your data, someone gives you a matrix, maybe it's compressed a little bit, and then you want to output some feature of this matrix, like an eigenvalue or something like that. And these are the problems that we kind of want to solve today. These are traditional linear algebra problems. But in order to get quantum advantages, what we've actually learned, and this actually applies to most of the quantum advantages out there, including factoring, I'll explain in a bit, is that really you're changing the input model a little bit. So even, there's this quantum linear systems algorithm that's very famous, HHL, right? And so the idea there is that, we can get possibly exponential advantages for solving linear systems, but it's not the linear systems problem we're used to. It's actually called something else. It's called the quantum linear systems problem. And the reason for that is that you don't specify your input directly as a matrix. What you instead have is some succinct or indirect representation. So you have some small object that's indirectly representing some exponentially large object. And then, on that implicitly represented object is where you're getting the advantage. And so, you kind of see how quantum mechanics could help there again, because, you have this large search space and nature is kind of keeping track of this exponential search space for you. And so, we really want to take advantage of that. And so examples of this are, again, the quantum linear systems problem works like this. Factoring even works like this because implicitly you're solving discrete logarithm, or you're solving a problem over some implicitly specified exponentially large group, in terms of input size. This also is true for physical simulation problems like local Hamiltonian. Someone gives you a compact specification of an exponentially large matrix, and then you want to answer questions about that. So this succinct representation kind of is important. And the message here is that even if we focus on conventional problems for utility or advantage, maybe we have to think about them a little bit different, if we want to understand where these quantum mechanical advantages come from. Okay. So I also mentioned earlier that, previously I was talking about unconventional inputs or unconventional ways of thinking about conventional problems, but I alluded earlier to maybe we want to even think about, different resources, like maybe space or memory, by space, I mean like the number of bits or the number of qubits you need to solve your problem. So, okay, so let's think about space instead of time. So if space is really your bottleneck, then, how do you quantify this? And in what settings does minimizing space actually help? So, even classically, people really care about space efficient algorithms in the wake of massive data, right? I mean, you have so much data, you can't really even look at it all. And so ideally, you want to make some informed prediction just by looking at a small piece of it. And so these are called sublinear algorithms. They don't even look at the whole input. They look at maybe square root of the size of the input, or maybe even logarithmic in the size of the input, and say something intelligent. But in the quantum case, space is actually arguably even more important, because developing robust, scalable qubits is tough, right? And so if we have quantum advantages that use limited numbers of qubits, this is fantastic, especially in kind of the near term or early fault tolerant regime. So even if you care about time, maybe you still want algorithms that use, given that they run efficiently with respect to time, they use as little space as possible. So space is really well motivated for quantum. And now we just have to kind of decide, how we're going to construct problems where we could get space advantages. So when you're talking about space advantages, it's really important how you specify the input, because if someone just has all of the data, then a space advantage, is kind of cheating a little bit. Like if you've stored all of your data, why does it really matter that I only use logarithmic space to process it? It's already stored. So are there models where you're not explicitly storing all of your data and then you can get space advantages? So one such model is the streaming model. So this is what we're going to see. Is this an example of a advantage with respect to an unconventional resource, but also kind of an unconventional but important model of computing? So in the streaming model, your data is built up by a number of small updates. And these things have been studied for decades. You can imagine lots of examples. I'll give you a few. But the idea is you get these pieces of data one at a time. And each time you see a piece of data, you've got to, update the state of your memory, of your algorithm. And then you never see that piece of data again. And then at the end, you have to answer some question about what you saw. So, this is well motivated by the internet. You have tons of traffic flowing. You can't, probably store even like a month's worth of internet data and hope to do something useful with it. So you really want to do this in real time. You're seeing all these packets fly by, but your router has, super limited memory with respect to the size of the total amount of data you'll see. And so these kinds of applications motivate it. Something else is social networks. You only hear that people are friends or enemies, maybe one at a time. And so you have this implicit graph, but you're only seeing kind of one edge or the deletion of an edge, happen at any moment in time. And you just have to kind of piece this graph together, based on all these updates you're seeing fly by. Other examples include sensor networks. You have sensors out in the field, they're just generating kind of a lot of data in real time. And you're not really storing all of it because your sensors may not have a lot of memory, or, it may cost too much power or whatever. So there are a lot of applications for streaming algorithms, and they've been studied independently at the labs and more broadly, for decades. And then we could ask, well, what about quantum streaming advantages for graph problems? So this is great. This is one of these stories where early on, relatively early on, we know that there are, or we've known that there are kind of exponential provable advantages. So this means that we know that, if you care about how much space you're using in the streaming context, there are quantum algorithms that use a logarithmic number of qubits and classical algorithms that'll need like root n bits. And, any classical algorithm will need that much. And so what this is really saying is, no matter what kind of classical hardware I build and what kind of classical algorithm I run, there will still be an advantage if I use, quantum mechanics in my computer. And so this is exactly the kind of thing we're interested in. But the only hitch here is that this advantage was for a very contrived problem. You know, in fact, in the years since this problem was discovered, its only application has been proving this advantage. You know, it's called Boolean hidden matching. And so an open question after this work was there any kind of, you know, is it possible to get advantages for problems that we actually care about and you know, problems we've actually studied classically? So the first kind of result in this vein was pretty recent by someone we hired at Sandia a few years ago, John Kelleher, and he, you know, just even this work started as part of a class project in Scott Aronson's quantum computing class, but he ended up discovering this, you know, advantage for counting triangles in graph streams, which is actually a really important problem, you know, in analyzing social networks and other kinds of networks. So this is great. So there's this advantage for a natural problem, but it's only polynomial, you know. And again, so that means that maybe if you actually implemented this, you know, the advantage would be washed away by overhead. So then we started looking at maybe for optimization problems, maybe for like well-studied problems like max cut. I'll tell you about that in a second. You know, you might be able to get quantum advantages. And unfortunately, we proved that it's impossible to get a quantum advantage for max cut, you know, which was a little disheartening, but at least we know where not to look. And so we kind of gave this up for a while. And then, you know, I don't even remember exactly why, but we looked at directed max cut. So this is very, very similar to max cut. It's just max cut on directed graphs. And again, I'll explain these problems and the motivation for them in just a sec. But it turns out that if all you do is look at this problem on directed graphs, all of a sudden an exponential advantage is possible. And, you know, this is the first exponential advantage for a natural problem. And actually, it's also the first quantum approximation advantage. You know, people have been looking at quantum for quantum advantages for approximating discrete optimization problems, you know, for a while since the quantum approximate optimization algorithm came out in 2014, and there haven't been any kind of you know, rigorous results. And this is sort of the first kind of approximation advantage that we know, albeit it's in the streaming model with respect to space. You know, it's not a time advantage. So the message here is you know, the search for quantum advantages is maybe even trickier than I may have led you to believe, right? Because look, if I looked at max cut and that was the problem I cared about, I would have said, well, no quantum advantage is possible. But this adjacent problem, which arguably has even more applications, you know, there's an exponential quantum advantage. So, you know, the message here is maybe instead of like really focusing on the problems we're already solving, you know, we should leave a little bit of leeway and try to understand where quantum mechanics actually gives you an advantage. So the last thing I want to do before I present the PRDs is just tell you a little bit about, you know, how this advantage works and what the problems are. So max cut is someone gives you a graph, and you know, the running example you can think of is this is a communication network. So an edge means that two nodes are communicating. And what you want to do is you want to find a set of nodes where the communication to the rest of the graph is maximized. You know, so you want to understand, you know, which sets of nodes are responsible for the maximum amount of communication, external communication. And so another way of thinking about that is you want to sort of color your nodes blue and orange, and then you want to count the number of edges that cross. You know, that's the communication between these two pieces. And you want to maximize that. So in this example, there's 7 edges cut. This is an NP-hard problem. And so, you know, probably the first thing you do is not going to work, at least on large instances. And so it turns out that actually there's a way of getting 12 edges cut. So, and that's the maximum cut in this graph. So the directed version of this problem is now, you know, your communication is directed. So you could, and this problem is more general because if you wanted bidirectional communication, you could just put, you know, directed edges in both directions between a pair of nodes. So this is a strictly more general and harder problem than max cut, but this allows you to model one-way communication. You know, so the problem you're talking about here is you want to find a set of nodes where you're maximizing the outgoing communication. And you could also think about this problem in transportation networks. And there, you know, directed edges are useful because they allow you to model things like one-way roads, you know, which actually end up mattering in practice. So the directed version of the problem is that you only get credit for edges that kind of go from the blue nodes to the orange nodes and not vice versa. Okay. So like I said, these problems are hard to solve. So what we're interested in is how well we can approximate them. And the approximation measure here is sort of, I have an algorithm, it's outputting an answer, and what fraction of the optimal did I earn on that answer? So I'm kind of, that's how I'm measuring the quality of a solution here. And so it's really easy to get a half. You can just kind of randomly assign nodes, and this is for the undirected version. You can just randomly say, your node is either orange or blue with 50-50 chance, and you get this trivial approximation. And now again, we're looking at space advantages in the streaming model. And so classically, people knew that you don't really get anything. You have to look at the whole graph. You need linear space. And so you need linear space to get anything better than the trivial algorithm. So really, there's just nothing you can do here. And we proved, that this is the same for quantum algorithms. And so there's just no hope for an advantage here. But what happens in the directed version of MaxCut is that now, this trivial algorithm only gets you a quarter, approximation factor. So the quality of the algorithm is only a quarter. And so now there's a little bit more room for an advantage. So getting, better. So yeah, let me say it the way I presented in the slide. So if you want some approximation between a quarter and 4/9, then both classically and quantumly, you can do this using, a polynomial in logarithmic, a polynomial in logs of n. So this is kind of a reasonable amount of space. And then if you want better than a half, the previous result kind of applies, and you just can't, you need to look at the whole graph. But what ends up happening is that by making this problem harder, looking at directed MaxCut instead of MaxCut, there was this little bit of room you created where classically, you need square root of n space, but quantumly, you can still do it in polylogarithmic space. And so making these problems harder, or looking at these indirect, this is also what happens when you look at those indirect input models I was talking about. You're implicitly making problems harder. And so you're creating these room, creating room for these quantum mechanical advantages is one way to think about it. So, I already mentioned this, but people have been looking for these approximation advantages for a while. And, this is sort of the first kind of example of this, but not in the standard model, So anyway, the takeaways here are the grand challenge itself may have seemed kind of mundane and expected, but there's actually a lot behind it, right? So there's a lot of nuance here. And so, these are all things that we considered when we were coming up with our priority research directions and the context around them. So we really want to find, we want to cast a wide net and looking for advantage. So we want to not just fix a particular resource, but we want to consider, any resource that could matter where an advantage is possible. And like we said, advantages are highly sensitive to how you specify the input and even how you specify the problem. And so we've also got to be mindful of that. And then, the question that this really raises is, are we just missing important quantum advantages because we're really focused on the problems, we're already biased to solve and that we're already solving? And so should we be looking at more kind of creative adjacent problems, for quantum advantage? And so I know I said earlier if people had questions, but, this is maybe a good place if there are questions on any of the stuff that I just mentioned, or comments, I'm happy for that. Yeah, Gil, please.
Yeah, nice presentation. Do you believe that the pursuit of random circuit walks and boson sampling was helpful or harmful, to the goal of trying to find useful algorithms other than molecular simulation and destroying the world economy?
I don't know. Personally, I think it's helpful. Like, I think anytime you find a new kind of quantum advantage, I mean, okay, right. So yes, I mean, there's this issue of what kind of, broader impact these stories have and how people construe them and, what people do with them. But from a scientific point of view, I think it's exciting just that we have new avenues and actually, sampling, I mean, chances are that even utility demonstrations will ultimately rely on some, there will be some that heavily rely on sampling tasks. And so, opening the door to those is probably important. Thanks for that. That was a good question.
Hello. Yes, this is Marianne Leung. I have a question or kind of an observation. Really wonderful presentation so far. In terms of looking at problems to solve, which I can see as really important to get the right kind of problem and appreciate the directed graph example. I'm wondering, there's a lot of classic NP problems in different spaces, scheduling, configuration, or is your team looking in some of these areas as well?
Yeah, actually, thank you so much for mentioning that. One thing, one thing I forgot to mention here is that actually, in a longer version of this talk, I kind of have a slide that gets into this, but the issue really is that with NP-hard problems, so if we want, it's the same story we see classically, right? It's that if you want rigorous kind of advantages for NP-hard problems, basically forget about it. I mean, you can approximate them. That's where these approximations come into. And yes, the answer is, certainly we're looking into approximating NP-hard problems. I mean, this is something that a lot of people are looking into. But, for solving NP-hard problems, you just, you do what we do practically. Somehow the instances we encounter in the real world aren't barriers, or maybe we're self-selecting and only in solving the instances we can, whatever your story is. You could also apply that quantumly and say, hey, maybe I'm just happy if I get some kind of empirical indication, that there's promise on NP-hard problems. But then it goes back to what I said earlier about, we might be ignoring opportunity costs, or we might be ignoring like scalability. Do these empirical advantages persist as the problems get harder or the instances grow in complexity? So yeah, I think NP-hard problems are what people care about, but we just have to be careful how we consider them. And I should also say that when you actually, thank you so much for raising this, but back to this slide, this I thought was really interesting, is that when you present a problem in the conventional way, so like if I present a conventional instance of max cut, where I just give you a graph and then I say, hey, find the maximum cut, that's NP-hard. But if I give you a succinct version of that problem where I just say, hey, I'm giving you an algorithm that can test if two vertices are adjacent, but the graph it's representing is really, really much, much larger than the size of the algorithm. Or I give you a small amount of data that's representing an exponentially larger graph, and then you want to solve max cut in that graph. Well, it turns out that the complexity of those problems get even harder than NP. They become hard even for quantum computers, which is QMA. And so this is actually some of the rigorous reasoning of why quantum mechanics kind of seeps into these problems. And in fact, there's another result, another kind of body of work that we're working on. It's very interesting. Right now it's just based on some simple observations, but there's a way of taking a graph that someone gives you and constructing an exponentially larger graph. And it turns out then, like, the local Hamiltonian problem, which is a cornerstone quantum simulation problem, just can be explained completely classically without any quantum mechanics, just in terms of, if someone gives you a graph, use this, very simple construction to construct an exponentially larger graph and find maximum eigenvalues there. And somehow that problem, is a cornerstone quantum physical problem, even though we said nothing about quantum physics. So NP hard and harder, is what we're looking at, because some of those harder problems matter for quantum simulation.
Yeah, because I was thinking like in the classical, traveling salesman problem, there's a lot of solution space that, you can't get to all of it, but it seems like the quantum algorithms could, tackle that in the ways you described.
Yeah, that drives a lot of intuition behind quantum heuristics, certainly. Okay, great questions. Anyone else? Okay, so then maybe in the remaining time, let me tell you about the priority research directions. So, these were, again, going back to just 5 levels of sort of a basic, a generic computing or networking stack. So the first research area is software tool chains, right? So we need end-to-end software tool chains that are going to enable kind of implementation of these scalable algorithms. And this involves a lot of stuff, programming languages. You don't just want programming languages that kind of capture quantum computing, but you want them to be expressive enough. You want them to be user-friendly enough that people will actually use them and are kind of productive with them. you also want to make sure that whatever tool chains you're designing, you know, are able to kind of realize quantum advantage and are integrated across the stack. So one theme you'll see with all these research directions is we take kind of a, you know, holistic view of the stack, and we want kind of tight integration. And you know, a similar story goes for the networking side. All right, and so I here, you know, I've already talked about most of these points. Let me see, is there anything? I think I've actually covered all of this, but you know, we just want efficient algorithms delivering advantages and ultimately utility. But again, you know, the maybe the thing to mention here is that I was alluding to this in the beginning. You know, you do want kind of tight integration with your programming languages, you know, with your resource estimation, with your benchmarking, with your architecture, and so this priority research direction kind of entails that. And speaking of benchmarking, you know, there are lots of different kinds of benchmarking, right? So you want to benchmark actual algorithms, you know, in a way that's agnostic of hardware, but you actually need to make sure that your quantum hardware is doing what you think it's doing. You know, you also need to come up with right metrics that aren't misleading you. This has been very tricky. You know, this is, yeah, I mean, I could say a lot about this, but won't here in this context. But you know, this ends up being very challenging. So you know, and this again gets more challenging when you look at the stack. You know, and basically, I'm going to say this for all of these is that, you know, when you look at this integration, there's some opportunities there for sure, but there are also challenges, right? And then you know, of course, the big one or a big one, you know, how do we deal with noise, and how do we deal with noise at all levels of the stack, and how do we deal with you know, noise in kind of creative ways, you know, not just maybe the standard ways. Are there other ways to design noise resilient algorithms in the near term, you know, other than using like just full fault tolerant quantum computing? And quantum networking is actually a very interesting example because you know, I'd say it's underdeveloped with respect to quantum computing, right? I mean, in quantum computing, we kind of have Shor's algorithm, you know, at least giving us, you know, it's our beacon of hope, right? This is something we think we can do that has, you know, implications for the world we live in. But for networking, you know, we have some examples, but they feel more like one-off things. And we don't really have any kind of, you know, what I would say are asymptotic or scalable kinds of things we want, you know, we're thinking about advantages on. I mean, some things that I've heard are maybe for detecting dark matter, you know, quantum networks are important and they give you a little more accuracy. But, you know, in the same way that we're looking for scaling with respect to some resource for like Shor's algorithm or something like that, are there problems in distributed quantum computing, you know, where we can have advantages? So the streaming stuff actually points to this a little bit. I mean, it turns out that streaming is actually related to something called communication complexity, where, you know, it's kind of like just a simple model or looking at kind of, you know, one aspect of distributed computation. So here, when we say quantum networks, this covers a lot of stuff, I should mention, you know, so this is, if, you know, everything from kind of raw entanglement distribution networks to higher level things like distributed quantum computing. And so, you know, the idea that everyone kind of thinks of when you say distributed quantum computing is, oh, you know, it's hard to kind of build single large quantum computers. Can we build like lots of smaller ones and somehow still get some kind of advantage? And maybe, you know, so these are the kinds of things that we're looking at here. And so aside from all of the things we mentioned for quantum computing, a big one here is also to find some killer applications. So that's my last slide. So let me just open the door to any additional questions that folks have.
Yeah, questions, please. Valerie?
Let's see. Thank you. I enjoyed your talk. I was wondering about PRD1 in terms of the software stack, and just was wondering, especially if we consider systems that have, you know, HPC systems connected with quantum systems, if the software stack that you're looking at in PRD1 is inclusive of that type of environment. So looking at having also an integrated stack that would be inclusive of a HPC and quantum system?
Yeah, thank you for the question, Valerie. That's excellent. Again, all these questions are helping me fill in gaps and things I wanted to mention but forgot to. Thanks for reading my mind, everyone. So yeah, absolutely. Hybrid, another theme throughout the PRDs are kind of hybrid methods, like we don't want to go, maybe it doesn't, maybe we want to kind of ease into quantum by taking advantage as much as we can of classical resources. And so, of course, designing kind of a stack that incorporates both has its own challenges. And yes, that's definitely included. The report talks about that, but I didn't mention it explicitly here. So thanks for that.
Thank you.
Yeah, Marianne again.
Thank you. I really appreciate the presentation and the great work that you guys are doing. And I'm just wondering, well, of course, that your focus is on the technical aspects, but I wonder if the project is looking towards building the future, which of course requires a look at workforce development,
Yeah.
because in order to have a great quantum enterprise, we need people to work on it.
Yeah, absolutely. Absolutely. And this is, I believe we mentioned this in the report, but yeah, like, and this also ties into Valerie's point about kind of, hybrid approaches is we want to create as many opportunities as we can for kind of short paths, for applied mathematicians, computer scientists, et cetera, without prior expertise in quantum mechanics or quantum physics to be able to lend a hand, right? And so, these kind of hybrid approaches definitely do that, but there are other ways too. And in fact, I'm a computer scientist, and I got into kind of quantum algorithms, I guess I say recently, but by now it's been a long time. But I've never taken a quantum physics class, and it's been a lot of fun, but also challenging kind of diving in. A lot of times, I mean, I understand things that's kind of a mathematical level, but the intuition completely escapes me. And then, years later, I'll learn the intuition and I'll be like, oh, this is fantastic. Like, why can't I just open some book and find this somewhere, but yeah, so I think a lot of us have similar stories, and the great thing is, like, this pain of this pain and pleasure of kind of diving into a new field, we understand well enough that we can kind of help other folks ease into it. And so this has been an explicit viewpoint in kind of crafting the PRDs. So they're again, just to summarize, other than kind of hybrid approaches, there are lots of opportunities to engage applied mathematicians and computer scientists and give them kind of a scalable way to get into quantum. So hey, look at this isolated piece of problem. I'm giving it to you in a way that you don't need to know any quantum mechanics. In fact, that was one of the motivations for this alternate characterization of the local Hamiltonian problem that I was telling you about earlier, is that I wanted to explain this problem in 5 minutes to people at a conference, who knew nothing about quantum mechanics. So yeah, we're very mindful of that.
Actually, let me clarify. I was talking about engaging students and
Okay. Oh, I see.
and younger people to get interested in going into the field of quantum computing.
Yeah, I mean, I think a lot of that, I find that generally, junior folks are pretty interested in quantum just because of what you hear, right? And so, yeah, I mean, we, in most of our ASCAC projects, we definitely have found ways to engage students. I mean, but I think this is what everyone's doing, so I don't, I would love to talk to people and find more ways to kind of engage folks, but the usual suspects are certainly things we have on our mind.
Samir.
Samir Shende from Paratools and University of Oregon. I was wondering about the work they are doing at EPCC and LRZ in Europe in using OpenMP as a way to program these quantum devices. And they're looking at LLVM compilers and OpenMP offload to target these accelerators. Would that more readily integrate with our HPC ecosystem, as Valerie was suggesting? And do you have any thoughts on the feasibility of such an approach?
Yeah, so that's I'll say, I'll say something about that, but just the disclaimer that isn't my area of expertise. But I know that there have been a lot of projects that try to leverage. I mean, I think this is something that people, designing tool chains really want to do. You want to leverage kind of existing classical resources and general tools for designing programming languages and compilers. And so I know of many projects that kind of use LLVM at least. OpenNP, I've seen a few, but again, I'm not sort of, up to date on the literature. I think it sounds good to me, but I mean, it's also not going to be, I mean, you can get part of the way there, but of course you'll need to design something else to actually, control your quantum hardware and make sure you're actually doing what you need to on the quantum side. So I think the short answer is that, maybe if we generalize your question, yeah, certainly we want to leverage as much classical infrastructure as we can, and I think people are already doing that, but that won't get you all the way there.
Thank you.
We have a question online from Teresa.
Hi, very nice presentation. I also have a question about PRD1. Actually, it's kind of more of a comment. There's a little bit of the wild, wild west going on with quantum computing and the software stack right now, right? And what rightly so, I think, because it's still an emerging field and still trying to figure out how things are going to work. So I imagine you had discussions about how to make sure that software stack doesn't get locked in too early, if you know what I mean.
Yeah.
And yet make it so it's productive. I think that's, you got this really interesting tension between these two directions. So did you talk about that at all?
Yeah. So I think, our toolchain experts, this is something that definitely comes up in discussions, and that's exactly what I was going to say, this sort of tension or trade-off between, you want momentum towards you want convergence towards something, universal, but at the same time, you want to kind of make sure that process goes like slowly enough that you're converging to the thing you want, maybe adiabatic convergence or something like that. But yeah, I mean, it's, I wish I could say more. I mean, yeah, we're mindful of it. I don't think we have any kind of great answers. I mean, I think your understanding of the community is sort of, where we're at. But yes, this is something we're explicitly considering. And I think the report also talks about this.
Okay, thank you.
Just to kind of wrap up, there was one question online, and it's a question I would like to ask too, which is, what's the timeline really, do you think? I mean, I talked to somebody I know who was a theoretician in this area about 10 years ago, and he said, well, more than 10 years. And so the question is, what, I mean, are we, if we try to plan realistically for what future systems should look like, or think about what future systems should look like, what's your sense of what has to happen over the next time interval for something to be realistically usable, say in the sort of context that you're thinking about?
Yeah, I mean, that's a big one, right? Or the big one, maybe even. I think it really depends on your goal. So if your goal is that you want to see, some kind of empirical evidence that you built promising hardware, kind of like I was alluding to earlier, I feel like that's already happening and will continue to happen. If you really want to see, so this ultimate goal of seeing an example of quantum utility that's actually based on some rigorous quantum mechanical advantage, personally, I feel like that's going to require, a good chunk of fault tolerance, right? And so then who knows? I really don't know. I mean, I don't have any more insight than the community, and I think the community is still sort of up in there on what the impact of noise is on these kind of rigorous advantages. There's been some work recently that kind of shows that, theoretical work that, noise can actually make things classically simulable, in kind of an understandable and predictable way. And so, maybe this is kind of also what we believe, kind of noise makes things more classical. And so I think that's the main tension. And, I don't think we have any kind of, we don't have any sort of path to kind of this all-encompassing sort of quantum advantage that doesn't need some degree of fault tolerance. And so that's still a big research question, whether we could do that or not.
Okay, thanks very much, and thanks for a great talk and a great answer. Thank you.
Thank you all.
Okay, let's let's move on to Ben Brown, please.
Is there a slide advancer here or do you? Okay. Well, I am the second half of the division director duo for the meeting. So thank you for the opportunity to give you an update on FY24 highlights and happenings from the facilities division. So I know we're a little over time. I was already going to struggle to hold to my time. I'm going to double that effort to wrap in 30 minutes with a little time for questions. Next slide, please. I want to begin with some special aspects of FY24. It really was a barn burner of a year. I have a preserve of some space to acknowledge some really seminal highlights from each of the facilities, but I want to also talk about some of the cross-cutting strategic efforts that we've had this year and end with just an open invitation to talk a little bit about the future. I don't think we'll have a lot of time for that, but you know where I live and we can talk in deeper conversation about that. Next slide, please. I know this is a wall of text, but I'm going to walk through it. This was a really amazing year. It was dynamic, to say the least. I want to spend a moment on the very first bullet. There's an enormous amount of effort behind the scenes with the teams when they're working on a major upgrade project, both in the NNSA ASC program that you heard from Cy Hammond yesterday and our Oscar facilities. So I've listed a number of projects here, and this bullet can't possibly encapsulate the sweat equity of the teams to engage with vendors in the long gestational period to get to the point of releasing an RFP. But this was a highly, highly dynamic moment. As we all know, computing technologies and roadmaps are evolving rapidly. And yet we have several systems sort of crunched from the pandemic era, kind of time synced as boxcars. And so we've done the huge credit to the teams at the labs to coordinate together to ensure that the vendors weren't seeing RFPs at the same time, multiple RFPs at the same time. But really, this bullet is trying to acknowledge that the work to get the vendor community synced with the mindset of what our teams are looking for and vice versa, the converse of that, to be receptive to what the vendors are interested in working on is just untold hours of work. So that's what that first bullet is about. You heard in May about the Office of Science Facilities charge. I'll have a couple of slides on that. This is a once in a decade event. So that was another special thing about FY24. We also launched the Integrated Research Infrastructure Program, which you heard an extensive briefing in May about that. We selected and stood up the High Performance Data Facility Project, another once in a blue moon, the prospect of a project, if it's successful, to deliver a new Oscar facility, highly unusual, special year in that regard. The National AI Research Resource Pilot, NAIR pilot, you'll hear momentarily from Katie Antipas with a cameo from me about that effort. Again, not something that we've done in recent years, a major strategic multi-agency new effort. We advanced our strategic planning for software stewardship. I have a slide about that towards the end and want to celebrate the effort of that group. We delivered our Oscar Leadership Computing Challenge allocation program into the exascale era, which also was really challenging as we work to accept and deliver Aurora into open science. It was a particularly challenging year, and I want to celebrate, especially I want to name Jordan Thomas, who has been wearing two hats as nurse PM and her old job as ALCC PM as I've been working to backfill that position. So I wanted to acknowledge her efforts. And at the bottom, I know it's a lot to say, but this didn't even acknowledge job one. So scores of people at the facilities, the engineering teams, the user engagement teams that work day in to day out, the project management professionals embedded in our teams, and the ecosystem of professionals around our teams at the DOE National Labs at Argonne, Oak Ridge, and Berkeley. Again, I can't do justice to the level of effort there, but in this very fast-paced presentation, this is my slide of being sure I hit some of these notes that I didn't want to leave unsaid. Next slide, please. So you know this, but I just wanted to acknowledge this is a profound report. It's going to take us a while to really let this sink in. If you go to the next slide, you know, the high-level recommendations from the report, I cite them often. Jaren and I talk about this. Certainly, recommendation 3 about vendor engagement is really an all of Oscar recommendation. And so I just wanted to begin with a note of acknowledging, I fully anticipate 10 years from now, we'll still be talking about this report. And it really is informing our thinking in a lot of ways. Next slide, please. So when we think about those upgrade projects, yes, 2 slides ago, I showed that table. And of course, a very plain vanilla approach to the ASCAC charge would have been just to focus on the major upgrade projects, because each of them alone is a substantial investment and undertaking. we wanted to, as a team of the Oscar Facilities Division, wanted to give the community just this snapshot view of the plan of record for the deployment of major systems. I'm not going to spend much time here, but just to illustrate that we are on track and we fully anticipate that Aurora will be ready for open science in 2025, calendar year 2025. And I'll note also that the NERSC team is working extremely hard on the NERSC 10 system timeline. And this is really a byproduct of also the pandemic era, that we anticipate needing to extend Perlmutter, having a bridge system for the NERSC 10, and then having NERSC 10 operations come online in 2028. Next slide, please. Okay, now I'm going to go to rapid fire for each of the facilities. And you also notice on these slides that I put a little guardian angel picture of my team member up in the upper left. So ALCF, Sash Majumdar is the program manager. Next slide, please. Many of you know this, but I would be remiss not to signal this really high watermark ISC in Hamburg in May. The Aurora team took its place in the top 500 and #1 mixed precision benchmark. This was really celebrated. It garnered a lot of attention, obviously, in the trade press and around the world. It's really a high watermark for the Aurora team. It's been a long road, and we're feeling really good. Aurora is a monster machine. It is gigantic, and so we're still in the shakeout phase, but that's really going well. Next slide, please. I can't do this justice, but I think one of the things that's fascinating about the early science work using Aurora pre-acceptance is that using the scale of the system for AI is already paying dividends. So this just represents a pastiche. You've got magnetic fusion codes. You've got the neutrino detection, cosmic trigger or cosmic tagger work. You've got extraordinarily high throughput drug screening inference, and brain mapping. So, I mean, there's many other things going on, but just to give you a bit of a sense of the diversity of early science that's going on at Aurora is quite compelling. Next slide. Another hallmark at ALCF is the AI testbed. I'm going to touch on this again during the NAIR presentation, but it's been a really significant contribution that ALCF has been building for years for the open community, is to provide platforms for exploration of advanced hardware. And so this is emblematic of the direction we want to keep moving, and across OSCAR with the ACT division and our work with the research division of providing venues where the community can explore this new hardware, but with the context of a collaborative spirit with our major HPC centers. And they continue to build out this AI testbed and renew some of the hardware as the year went on. Next slide, please. Okay, shifting to Oak Ridge Computing Facility, where Christine Chalk is the program manager. Next slide, please. You heard yesterday, of course, from Bronson, so I don't have a science highlights piece here, but I did want to mention this is a special moment for the Summit system. Summit, I've learned from the wise old hands that system to system, you just never know which ones will be just rock solid, and Summit is one of those rock solid systems. We decided with Jaren's leadership and Oak Ridge to extend the lifespan of Summit by 1 year. This was a consequential decision. It was something that took real resources, but was also something that unlocked potential to advance AI research, some early IRI efforts. And the Oak Ridge team did a bespoke Summit Plus allocation call at a cost of significant human effort. And we're really proud of that. I think that Summit Plus exemplifies wanting to make the best deliver on the taxpayers' prior investments, balancing the opportunity and the cost of extending the lifespan of a really powerful system. If you go to the next slide, we're about to decommission Summit in November. And so we just want to, this is a little pastiche. I'm sure there'll be other moments to celebrate Summit at Oak Ridge, but an extraordinary record. The Gordon Bell prizes, of course, are high watermarks that we all totally celebrate, but this system has been a truly impactful for science. Next slide, please. You heard yesterday briefly about the New Frontiers vendor program. So this is also something behind the scenes. You're probably sick of me saying extraordinary effort, but each one of these slides represents quite a journey. So I think the conversations around this approach started very early in the fiscal year. And we saw the opportunity to do something like this with Jaren's support. And we're excited that this is on the street. And it really is a new chapter in OLCF's approach and also the Oscar Facilities HPC enterprise approach to stimulating vendor engagements of a variety of sizes and longevities. Next slide. QCUP, the Quantum Computing User Program at Oak Ridge, continues to be a beachhead for organizing thought and approaches to exploring the nexus of QIS systems and HPC, exemplified by their annual user forum that you see a picture of here. Yeah, we can just continue to have this wonderful engagement and looking forward again with the stand up of the ACT division to mature Oscar's strategy for engaging QIS users and the connections between the traditional HPC users and those interested in exploring QIS systems. Next slide. ESNet with Carol Hawk as the program manager. I can assure you that tiny little baby is not on the payroll, but it's pretty sweet that she's there. Next slide, please. Okay, so I have a couple extra slides as a prerogative. For those of you who aren't familiar with ESNet, coast-to-coast and intercontinental network, one of only 2 research and education networks in the United States, Internet 2 being the other, 15,000 miles of dedicated fiber. Oh, actually, this is my previous slide deck, but that's okay. I'll speak to it anyways. I don't want to break stride. So we'll make sure to have the intended slides posted, but the next slide, which you don't see, is the classic up and to the right traffic plot. So if you're familiar with these exponential growth in traffic, yes, this is still a thing. There was a dip in the pandemic. We're at 1.7 exabytes transited ESNet in calendar year 2023. It's kind of insane. Next slide. The investment in the transatlantic links is actually only a fairly recent landscape feature for ESNet in its history, driven by the Large Hadron Collider in the high energy physics community, but also downrange looking to the ITER era. And I want to specifically credit the effort of ESNet director Inder Manga and a couple of his closest team members who worked for several years here to explore the potential of ESNet to acquire dedicated spectrum across the Atlantic. Essentially, this is a wholesale market question ESNet has never played in. There are big movers and shakers in the world of transatlantic, and it was something that ESNet is able to execute on this year, which we think is extraordinary savings for the taxpayer in the long run. Next slide. Yes, the ARES project. So we recently had a Super Lab 2.0 demo in September. So ARES is a collaboration leveraging ESNet that's the Office of Energy Efficiency and Renewable Energy and the Office of Electricity, I think prominently Office of Electricity, in which they have essentially real-time grid modeling tied to some digital twin assets and some physical assets. So this is another high watermark. This is a multi-year collaboration, but this slide just represents that ESNet has continued to be a rich partner in enabling this work, and the demos that they just had in September continue to lever up the sophistication and maturity of this research environment for the Department of Energy. And what we hope to do in the future is add many more endpoints in physical systems. Next slide. There's a couple of IRI highlights. So ESNet has been marching out, as you heard in May, to create in collaboration with the other Oscar facilities an IRI test bed, so that test and development environment for conceptual design of IRI technologies. This represents, I know it's quite techy, coast-to-coast detector to compute real-time streaming. So essentially, what they've demonstrated this year is generating data at JLab and throwing it across the network to NERSC in real time with no caching, and able to use this to demonstrate the technology end-to-end stream or architecture required to not have that data go splat and hit a wall somewhere. So we're excited about this as it demonstrates some of the streaming research workflows that we encountered in the IRI blueprint activity and that people have been working on for a while. Maturing architectural approaches that make those workflows performant, automated, and programmable is really what this work exemplifies. Next slide. There's a second one, a streaming example called Deliria, which represents a synthetic data generation context. So you can imagine the previous one was a real world example of real experimental data being thrown across the network, but in fact, you also need the ability to create synthetic sources and to kind of in that playground mindset of developing architectures. Next slide, please. Lastly, I just want to celebrate for a moment that ESNet, as they've grown their workforce through the ESNet 6 era, you may not know, but they are a highly geographically distributed workforce. I think they have employees in 23 states. And so the ESNet leadership has really conscientiously, coming out of the pandemic, devised a culture and engagement program that formalized, solicited, well, I should say, a year-long effort to engage the entire ESNet workforce in a values exercise to, this, larger workforce, this 100+ FTE team, the ESNet leadership really wanted to take ownership, have everyone take ownership of that. And I just wanted to celebrate that with this slide. Next slide. Jordan Thomas, nurse program manager in the nurse team at Berkeley. Next slide. NERSC turns 50 this year. Wow. So NERSC is an incredible powerhouse, over 10,000 users. We crossed over the 10,000 user threshold last year. And so if you are in the vicinity of Berkeley in the third week of October, there will be a celebration and a symposium at Berkeley Lab. I think it's October 22nd or 21st, if I'm not mistaken. I wanted to call your attention to the lower left. Of those 10,000 users, close to 50% are graduate students and postdocs. So not represented in these slides. I continually am amazed and impressed by the NERSC team as they think and try to critically understand the diversity of the user community that they engage with, how to scale their engagements with such a vast community, but also the very special thing in the Office of Science of such a large early career kind of baked in demographic. And I always think of our facility as sort of town halls of science, like places where people come to gather. And so I can't do justice to it here, but I'm just continually impressed with NERSC and how they continue to renew their approaches and thinking about how does the younger generation of scientists consume or what information do they want as they engage in their NERSC journey. Next slide. Again, how can I do justice? I mean, literally hundreds of scientific papers and dozens of highlights that come from NERSC every year, but the stargazer in me couldn't help but select, and I think credit Jordan and the team for this too, this gravitational lensing highlight, this carousel lens, Einstein cross highlight. I encourage you to take a look at this if you're at all into the night sky. It's just, or cosmology. It's just astounding. So the work that led to this, to being able to find this in the sky is quite amazing. In contrast, here's a use-inspired research example from synthetic biology, where a Nature publication resulted from this, where looking at conformational shifts of molecules that has a link to potential for drug discovery. Next slide, please. Right, and the D3D tokamak IRI example. So this is something that I can't remember if we signaled or celebrated in May. But the super facility project at Berkeley that was a forerunner of the IRI program, where they worked with multiple user facilities on advanced workflows, has really been paying significant dividends for the D3D tokamak, the flagship tokamak experimental platform for the Office of Fusion Energy Sciences. And what's encapsulated here in the lower right is essentially that the reconstruction, it's an inference calculation of the plasma state. Traditionally, when you do these tokamak experiments, there's this enormous flood of data. And traditionally, the D3D team and other tokamak teams around the world, the process of reconstructing the actual magnetic field that was present in the living plasma is a very computationally intensive quasi-manual exercise. And so through this collaboration, piping the data to NERSC and shipping it back, doing the analysis at NERSC and shipping it back, it's captured here in the numbers. Over 14 years, the D3D team had created 4,000 of these handmade reconstructions. And in the first several months of this collaboration, did 20,000. So this is another example of the power of these proto-IRI collaborations. Next slide. The next two slides represent conscientious efforts at NERSC to, in the AI era and the QIS era, provide structured, manifold structured approaches to engaging the NERSC user community for AI and QIS. So they call it AI at NERSC and QIS, or quantum at NERSC. And really what this is about is providing a number of different ways for the NERSC community to get either if they're neophytes to AI research, exposure to training opportunities, and then those who are more experienced researchers to have structured ways to engage with NERSC staff who themselves have expertise in AI as a gateway to the larger DOE community. Next slide. Similarly, quantum at NERSC has a kind of parallel approach. So I just wanted to again celebrate that NERSC has taken a conscientious effort with such a vast user community to provide this sort of overlay and structure with a couple of different programmatic approaches to engaging their community, and also to celebrate that they won the Hans Meyer Award at ISC, which is the best research paper, which was one of their their quantum team at NERSC provided a paper. I think it was about essentially looking downstream to the potential integration of a superconducting qubit large-scale QAS platform with conventional HPC. Next slide. Okay, I'm going to wrap the last phase of this presentation, signaling back to those cross-cutting strategic activities from the year. So in May, I'm not going to cover it here. You've heard extensively about the Integrated Research Infrastructure Program stand-up, and later today you'll hear about the NAIR pilot. Next slide. I'm not going to read this, but it is useful. A lot of lessons learned this year about, we're contemporaneously standing up IRI and the high performance data facility, and this could be natively confusing. So I've left this here as a leave behind for you in the community. HPDF is a project to create a new user facility. The mission of HPDF is stewardship of large-scale research infrastructure, high-performance research infrastructure for the data lifecycle. IRI is a program. It's a program meant to be durable, to steward the elements of the ecosystem to make these workflows performant across the Office of Science user facilities and beyond. Next slide. The stand-up of the high-performance data facility project this year as a substantial undertaking. I believe this is a photo from April at JLab of key members of the Berkeley and JLab team. So I won't read this, but I know it sounds like we had a meeting and we had another meeting and we had yet another meeting. And yes, that's really what the year felt like. But in each one of these, there's configurations of people coming together. One of the things I'm proud of on the federal side is that we now have what we formerly called an integrated project team. That's the formalism we have with all major projects that includes not only the lab performers, JLab and Berkeley Lab, the headquarters program, OSCAR, but also the federal site offices at JLab and Berkeley Lab, all working together in concert, building those trust relationships and meeting weekly to tackle the building of momentum towards critical decision one, which is the next major milestone for the project. Next slide. A high watermark of this year, besides also getting FY24 appropriations, which was significant for the project, going from $2 million at 23 appropriations, which was seed corn, to their first kind of slug of funds of $8 million, is that after that occurred, we were a little more free to kind of chart our path for the months ahead. And in July, with enormous credit to the organizers and Carol Hawk on my team, we pulled off what we called an IRI HPDF coordination kickoff meeting in Gaithersburg. The sticky notes represent this as an active working meeting. So we had over 100 participants, including headquarters program managers from across the Office of Science, leaders from a variety of the experimental and observational user facilities, and members of the HPDF project team and the IRI leaders in the OSCAR facilities, all coming together for a big level set sense making and working meeting. And so there is a report out from that meeting. You can email me. I'd be happy to provide it to you. Next slide. I think I'm coming up to the almost end of my presentation. This was a really significant, this simple slide can't do justice to the level of effort here. Sashira Majumdar, the ALCF program manager on my team, chaired our OSCAR facility software task force. This is something that I put in place at the beginning of the fiscal year, coming out of, as we looked at the ECP transition and all of our work within OSCAR. We actually have our own federal task force spanning the research, ACT, and facilities divisions. About a year ago, in conversation with the facility directors and within OSCAR, we took the decision to create a task force formally with the charge to develop a collective vision and strategy for a performant OSCAR facilities open software ecosystem. So this group will have a report as well, which is nearing the finish line. Under Sasha's leadership, organized into a variety of focus groups, system software, program environments, tools and libraries, IRI, AI software, and engagement with external stakeholders. And over the course of the fiscal year, really took a very methodical approach, building also on the efforts in the broader community with CAS and our emerging new era of software stewardship, to really look critically at what are the key areas in which the OSCAR facilities should be muscling forward, should be connecting with, into the new governance that we're trying to stimulate in the community. Studying recommendations are there for you to read, but essentially what we're looking to understand is what are the resources within the OSCAR facilities that we should devote with intention in this next era to these efforts. Next slide. And this is my last slide. So I'm just going to speak for just a moment. As we look ahead to the next fiscal year, it would be easy enough for me to say, yeah, every one of the things on the previous slides, we're going to keep going forward. But I think you could tell FY24, as I began this presentation, had a lot of new things, new stars in our firmament. And yes, I don't expect us to do another once in a decade facilities charge this year. But I think that, as I began to talk, is one of the framing one of the frameworks for how we're approaching strategic thinking this year. The thesis statement of an Oscar facilities ecosystem is something that's both true in deep ways today, when I talked about the vendor engagement work at the beginning, and how the Oscar facilities, the team members of the facilities work collaboratively in many different ways to advance their specific missions. There are ways in which we can mature and make that kind of above the waterline that are some of the earliest efforts that I think we'll take with science engagement, with requirements gathering, as we look ahead to the future. So I think, hey, I think I'm going to rest there to take your questions for a few minutes and hopefully we get back on track with time.
Yeah, let's take some questions. Marianne?
Great presentation, Ben. Just a really quick kind of question comment. I appreciated that you shared at Nurse the data that have for students or postdocs.
Yeah.
I wonder if this data is collected and could be available to kind of take it to the next level down, like look at some of the demographics of those people and the institutions. What type of institutions are there? Minority serving institutions, so on and so forth. I don't know if this data. Yeah.
So the Office of the Deputy Director for Science Programs, where I used to work before coming to Oscar many moons ago, curates the user statistics guidance. And the good news is that there's actually been a very mature effort over the last 3 years to instantiate within the bounds of federal policy a finer grained resolution on some of the questions that you just asked. So that's a definite number one thumbs up. Number two thumbs up is that a lot of this information is already available on our website, and I'll email it to you on the Office of Science website. So the user statistics are publicly available, and there you'll see a pretty rich catalog of career station, institution. You can filter by project or by institution. You can even hit map views. You can kind of go to town. So I'll be happy to point you in that direction.
Perfect. Thank you.
Yeah.
Any further questions? Just one quick one. So the challenge now in the AI space is that software is becoming one of the key differentiators with regard to the hardware that people buy. DOE has been in a position where it has big software efforts in many areas that allow it to have its own software ecosystem to some extent, and that ecosystem goes out to other people. How does DOE do this, do you think, in the AI space, where the situation is kind of dominated by one or two companies and they have significant software efforts, which kind of, draw users in a way that is different from the past in some sense?
So some of what I'm about to say may sound sort of glib, and I don't mean it to sound that way. There's clear differentiation in the marketplace with the power of a vertically integrated software stack and the tools that users find appealing. And so from that standpoint, we would be foolish not to acknowledge that and leverage that. At the same time, there's a powerful history in Oscar of driving towards diversity, of a healthy ecosystem of software options. And of course, ECP is a high watermark for there, but I think all of the work in the software, the federal Oscar software task force, which Hal has led and we've been a part of in the facilities division, and CAS and the work of our task force in the facilities, led by Sash this year, are trying to make sense of all of the levers that we can throw, ranging from our convening power as the federal mission owner to the specific statements of works in our system acquisition contracts and NRE. Yeah, every one of these levers, if they're thrown in alignment, can drive change more rapidly. But if we aren't intentional about that and strategic about that, then we will not meet our expectations for having the maximum impact in the world. So that's why I sound a bit, that's why I prefaced my weasel words of sounding glib, is that I think we as Oscar want to see that diversity come to life. And of course, we're excited about the manifold of technologies and hardware and software that we have today at the Oscar facilities, but we know that there's a broad sea of actors around that space, and that it's not for us to decide.
I don't think that's glib. I think that's a very wise answer. Thank you.
Okay, I think we're gonna move on. Again, as a reminder, we're going to answer the public questions at the end of the meeting. So we have Katie Antipus online, and she's going to tell us more about NAIR pilot.
Great, thanks, Jaren. It's very nice to be here. For those of you who don't know me, I'm on rotation from Lawrence Berkeley National Lab and serving as the director of the Office of Advanced Cyber Infrastructure at NSF right now. And so today we'll be talking about the NAIR pilot. I'm going to be joined by Ben. So hopefully Ben won't stray too far from the podium there. And so I just wanted to start is, NAIR is just one of a number of AI initiatives within NSF. I think because NAIR has, you could say, somewhat of a snappy name, sometimes people ask me if that's the full NSF initiative. And it's really the infrastructure component of NSF's initiative in the AI space, which includes fundamental AI research, graduate student fellowships, research for undergraduates, as well as investments in AI institutes. Let's get started here today on an update on the NAIR pilot. I just have a little bit of background information to get everyone up to speed. So as I think folks are probably familiar with, a NAIR task force was formed a few years ago that was charged with investigating the feasibility and then create an implementation plan for a vision for a national AI research resource. And this vision is to provide this national infrastructure that connects the research and education communities to the necessary computing and data sets, software expertise to really advance the AI ecosystem for the country. And there's 4 key goals that were laid out as part of the NAIR task force report. And those were to spur innovation for the country, to increase the diversity of talent in AI, improve overall capacity for AI R&D, and then to advance what here is referred to as trustworthy AI. And so, how did we get to a pilot stage? Well, it was really the president's executive order from nearly a year ago, October of 2023, that directed NSF and collaborating partners to launch a pilot for the NAIR. And so we, along with our partners, launched this pilot at the end of January of this year. And so, our challenge really was how do you pilot a pretty large vision? The task force report calls for nearly a $3 billion initiative. How do you pilot that with your existing resources or your contributed resources and a small amount of seed money? And so the strategy that we took is that we wanted to investigate all the major components of the NAIR that are described in the NAIR task force report, but at a smaller scale, obviously a limited scale. We needed critically to leverage partnerships and then really embrace what we're calling a pioneering approach here. Is we want to go out quickly and try things so we have some lessons learned. So in the case there's an opportunity to scale the NAIR, we're really prepared to do so. And so we brought together a number of partners from different sectors across the country. We have 12 other agency partners collaborating on the NAIR. There's 26 non-governmental partners that include some of the largest technology companies, as well as some nonprofits and small startups as well. Each of these organizations are making contributions to the NAIR pilot in kind or with existing resources at this point. In terms of the agency contributions, and there's a lot of agencies listed here, and the agencies are just contributing different parts of based on their own expertise. And so DOE and NIH are leading the NAIR secure thrust of the pilot. You'll hear more from Ben on that. A number of agencies are providing data sets or models. NSF and DOE are providing the agency computing. Multiple agencies are providing, software, educational trainings. And then all the agencies here are contributing to the governance, which includes a multi-agency steering committee, as well as sort of I would say a lean pilot program management office. And then there's right now, three working groups from the steering committee: at data and models working group, secure working group, and an education and outreach working group. So what are we going for here? If you look at the kind of the key element or the design of the NAIR pilot, is that there is a set of users, and these users include AI researchers, domain scientists that are integrating, using, or developing AI for their applications, and students and educators. All researchers must be based at a US-based institution. But the institutions are varied. They can be nonprofits, they can be universities, federal, local, or state governments, FFRDCs, etc. Those researchers access resources through a portal. It's up now. It's a lean portal, nairpilot.org, and then they can gain access and request access to a number of different resources. And so then, on the right here during the pilot, we are focusing on a lot of outreach and community design process. And then we have a number of different thrust areas. So NAIR Secure, we have a NAIR classroom effort, as well as it's become increasingly clear that many educators and professors, simply don't have the resources even to teach or train students in introductory courses at universities. We have some demonstration projects and then some community building and outreach as well. And so in terms of the goals of the NAIR pilot, what are we trying to achieve in this very lean pilot here? And we're piloting this activity with a couple of percentage points investment of the envisioned scale of the full NAIR. And so what we're really trying to do is demonstrate the value and impact of this larger NAIR concept. And we want to do that in two ways in this pilot stage. First is support some novel AI research that wouldn't otherwise have happened. And then we want to reach really broad communities. And so these are things that we are tracking. We are closely tracking the researchers that are using the NAIR, but also not just that they get an allocation, but are they becoming part, or will they become part of a kind of a sustained research community here? We wanted to also demonstrate some new collaborations across the agencies. I think we have a good start to that. And then we want to really gain lessons learned for the full design of the full NAIR. So we have a number of activities that are underway, and during this talk, I'll hit on many of these. So first, we have researchers can request and access resources. In many ways, this is the most visible aspect of the pilot. There's now just about 150 different projects that are supported as part of the pilot. But there's a number of other activities going on as well, and this includes the first awards through the NAIR Classroom Initiative. We have different demonstration projects that are demonstrating hopefully some unique capabilities that the NAIR could provide. Some outreach capabilities, and NSF has a funding opportunity in that regard. We've also formed a NAIR pilot subcommittee out of an existing NSF advisory committee. We have a couple of workshops. One that's just completed from the summer on trustworthy AI, and one is coming up in December jointly with DOE on the NAIR software stack. And then we are also working in the steering committee on a process by which non-governmental data sets could be contributed to the NAIR. And so with that, I want to hand it over to Ben for DOE update. So Ben, I'm driving the slide, so just yell out to me when you want me to flip here.
And I'm back.
Okay.
And I changed my glasses. Okay, so I can read. Clark Kent. Okay, so briefly, and thank you, Katie, for a privilege of a cameo in your talk to celebrate the DOE contributions to the NAIR pilot, which have been substantial up and down our chain in Oscar and into our facilities and through their line organizations. I'm going to kind of step through Oak Ridge and Argonne contributions. The Summit system, as I alluded to, with the extension of the lifetime of the system for 1 year, we contributed some percentage of those cycles to the NAIR pilot. And so the projects that have come to life through that effort are really interesting to see, because I think one of the powerful things that NAIR provides is, here's a new effort, very visible in the community, and we're eager to see, do we get new knocks on our door as in our DOE systems through that NAIR front door? And the other special thing about the environment at OLCF is then through the efforts that Oak Ridge has had with Veterans Affairs and NIH National Cancer Institute in the last years, they've developed what's called the Citadel secure computation environment. And so think of Citadel as an architectural wrapper with a full, fully matured, I think, understood risk environment, if you will. It's a little oblique. What I'm trying to drive is that Citadel is not just a bunch of hardware. It's the fully integrated socio-technical policy venue in which secure data workloads can be delivered to the leadership systems at Oak Ridge. So Citadel was born to host data containing PHI. And so we're leveraging that in the pilot projects that you'll hear about in a moment. Next slide. Also contributing to the NAIR pilot, as you saw on my previous slide, the Argonne Leadership Computing Facilities AI test beds. So in the roster or resource listing in the NAIR pilot website, you'll encounter both these contributions. And this is, as you heard me say before, really significant. I think it's been powerful for us to see in DOE that these are unique resources. You don't see others coming forward with this kind of environment. So we're proud to have those as part of the NAIR pilot. Next slide. And something I didn't mention before, but part of the NAIR classroom, for example, is the training, open training and engagement activities at some of our facilities. And so mentioning here that ALCF for the last several years has developed rather a really quite extensive set of training opportunities open to the community and targeted at students. So please spread the word. Coming up soon, beginning in October, is the next iteration of the Intro to AI-Driven Science on Supercomputers training series. So we're proud to have that listed under NAIR Classroom. Next slide. So then briefly, 2 slides on the larger NAIR Secure pilot effort. Susan Gregorick's office at NIH is our partner in crime, and of course in partnership with Katie and her team. And so there's really 2 thrusts here under the NAIR Secure pilot, both of which are really oriented towards what are the salient sociological, technical, and policy issues that we should carry forward into the design of the full NAIR. So we don't think of NAIR Secure as a separate front door. What we know is that there are scientists, they want to do things. And if some of those things trip over protected health information, PII, other tripwires about protected information, we need a way, NAIR needs a way, just as we as DOE, any resource provider has ways of managing risk and opportunity. NAIR will need a way to gracefully assess what the research project is proposing to do and steering the PI, if they're selected for a NAIR resource, to get productive as soon as possible in managing that risk. So on the left, in a moment, I'm going to walk through descriptions of 3 exemplar demo projects that are formally under the NAIR Secure pilot. But on the right side of the slide, what these bullets represent is that there's a quite rich conversation going on in the interagency space that NAIR provides around managing risk. And what is our lived experience with different research projects that have managed protected information in the AI era? So I'm really excited about that in particular as a way of documenting with multiple agency voices some of the salient issues that the AI research has to contend with. Next slide.
Just a second. Next slide.
Okay. So the 3 demo projects that, under the Nair Secure pilot, that the contributing agencies have put forward, really, we're on a short timeline. Obviously, the pilot has, more or less a 2-year timeline. And so in devising, which demo projects to select, it was a pretty organic process. It wasn't like there was an open call. What we were doing in the interagency was understanding which agencies are sort of ready to go with something that they've been eager to try, but maybe have been blocked from doing. So the first project is an NSF-NIH DOE collaboration that's really focused on synthetic data, creating a synthetic data generation toolkit in cancer research. So at the extreme scale, 30 billion rows of data. Oh, and I should mention, OLCF and the Citadel environment is critical to each of these 3 projects, which also leads to connecting to what I said before. To do work in secure data, other than the commercial cloud, you really have to be ready to rock, right? So the fact that we already had Citadel, that the Oak Ridge team has matured that environment, positioned DOE to potentially support these 3 projects. The second project is an extension of the DOE NCI collaboration, working with the SEER data registry and creating a synthetic data store resembling real-world data. One of the characteristics of this project is that it will actually, once the sort of technical generations of the synthetic data matures, a separate security team will then encounter that data and judge for itself independently whether it is actually achieved the privacy enhancing technology goals of the project. So just to compare and contrast the first 2, the second one stands out as that sort of, at the heart of the project is do the work and now subject it to intense scrutiny in the harsh light of what high standards privacy enhancement or privacy preservation policies might require. And the third is in collaboration with NIH National Center for Advancing Translational Sciences, NCATS, and it's actually more in the mode of the LLMs. So essentially, the project is about managing the very fraught questions around merging specialized, say, copyrighted material that a research institution might have subscriptions to, and melding that information set with a model training in an LLM context. So we all know the roiling sea of questions around copyrighted materials getting slurped into large models and not being able to extract it. This project is about managing risk in that terrain between copyrighted material that an institution might have access to, but wanting to meld that with the open information in these large models. I think that's it for my cameo. Am I right, Katie? Yes.
Yes, thanks.
Thanks.
Thanks, Ben. Okay, so I wanted to move a little bit to talk a little bit more about Nair's role in data. So clearly, data is incredibly critical for AI research. But what is really the role the Nair should take as an infrastructure with regards to data? And so, to start with, in the Nair pilot, each agency has put up, or a number of agencies have put up data sets that they think are of interest to the community, where they'd like to get more research communities looking at those or accessing those. And these are, data sets that the agency believes are ready for analysis. But clearly, we need to go significantly farther than this. This was just a starting point. And so, as I mentioned, the steering committee is working on a process for the criteria by which other non-governmental data sets could be linked to as part of the pilot. But if you go even further than that, and you take a look at what the Nair task force said in this regard, it's worth repeating here. And I think I'm going to start with what the Nair is not envisioned to do with regards to data. So, I mean, the Nair is not envisioned to define data standards for a particular community, which are obviously best suited to be handled by and defined by that community as standards continue to evolve. The Nair is also not envisioned to fund the specific collection of particular community's data sets. And perhaps that's sort of straightforward and obvious to this community, but we had many questions about that. And so what is the Nair envisioned to do here? Well, here's a few things that are highlighted in the NAIR task force is that you would set guidelines or criteria for data set inclusion in the NAIR, right? It would support a data search and discovery service. It should incentivize communities to contribute analysis-ready data sets, provide access to integrated computing and data platforms, provide access to restricted data sets, and then I think importantly, provide technical expertise and user support to communities that are driving their own curation efforts. And so with that in mind, for the pilot, we don't have the funding at this point to, move out in a large scale way in any of these directions. But what we have done in NSF is we funded a couple of demonstration projects in this data space that start to get at some of these themes from the NAIR pilot. And so one of these is the Pelican project. This is a project that co-locates data and compute through federation and caching. The National Data Platform, this is a pilot or a prototype you could think of for a search and discovery service that's also connecting, compute and data. And then SAGE is a test bed for supporting streaming data at the edge. And so these are a couple of demonstration projects that we have brought into the pilot. So then I wanted to go on to talk a little bit more about some of those NAIR pilot awards, our operations, and the opportunities that we have open to the community. So right now, the research and education community can apply for resources. They can go to nairpilot.org. And there's an open opportunity for educators to access resources, typically kind of think of Jupyter-like notebooks for their classrooms. There are researcher resources, and then there's sort of an etc. bucket, which is called data models and more. And so there's a number of computational resources that are available to the community. I don't think this audience needs any introduction to how these computational systems are allocated or how they serve the community. There's 2 contributions from DOE in terms of the AI testbed from Argonne, and then Summit. Summit is retiring now, but it took a number of projects in the open call in January. And then there's a number of NSF systems that are available to the community as well. But, I think both NSF and DOE have a lot of experience providing computational capabilities to scientists. Something that we're also thinking about in the pilot is how do we move beyond compute to look at different services that can become available to the community. So we know that the cloud computing providers, they provide not only compute, but a host of services, model access, inference services. And so those are available to the NAIR pilot community as well. So if you get access to one of those resources through the application process, you can use those credits on compute or some of those other services. Some of the other partner contributions are, interesting as well. So Anthropic and OpenAI are providing API access to their closed models. Grok and Sambonova are offering platforms where researchers can bring their own model and do inference on them. OpenMind here is a company that's providing a privacy-enhancing, privacy-preserving technology federated platform. And Eleuther AI is actually a nonprofit that has a lot of experience training large language models. And so they're offering a collaboration to the NAIR pilot research community. So the researchers can apply to use these. And I think one thing that will be really interesting for us to track is how are these services used by the research community? Are they popular? Do people like them or need them? Or does there need to be some things that are more custom for the science community? And in that regard, one effort we have in NSF, and this is actually not integrated into the NAIR pilot at this time, but it's an award called the National Deep Inference Fabric. It's backed by the Delta system at NCSA, and it allows the research community to kind of probe the internals of large-scale models. And so this, this could be an example of a type of service that the agency or NSF would integrate into the future, or other projects like this. So let's get into some details here on some statistics on the 150 projects. I'm going to linger here on this slide because I think it tells a lot of different stories here. So let's go slowly. What you're seeing here in this graphic is the 150 projects bucketed by their compute request size, and then a bucket for other, which I'll talk about in a moment. And so you can see on the far left, and I'll say these are all projects are all normalized to A100 GPU hours. So you can see the bucket on the left, there's 10 projects that have requested, allocations larger than 100K, so pretty large scale projects. And 5 of those are supported by DOE Summit. DOE Summit system supporting 8 different projects here. And then NSF is supporting over 100 different projects here. Let's see. You can also, let's talk about this other bucket here for a minute. This is that bucket of those etc. categories, some of those new services, some of the NAIR classroom activities here, model access, and some of the novel hardware. So the 6 ALCF testbed projects are included in here. And so, when I look at this graphic, this really, demonstrates and shows I think the complementary nature of the two agencies, where DOE is supporting, a handful of very large projects, and NSF is supporting kind of the large backbone of projects here, many of which are individually at a smaller scale. The other thing to note here is each one of these projects has a PI, right, and students. And so this is a future workforce that is getting access to these various systems. So then what are these projects here, I would say, that are in this middle scale, this 110K to 100K range? And that turns out, I think, to be pretty interesting. So I'm going to go to the next slide. And again, take a moment here to talk through this. So you're seeing 2 pie charts. And the pie chart on the left is the 150 projects, and a count of those projects. So nearly 70% of the projects are in the category of CS, AI, or intelligent systems. And so we did actually go through this. I said, now this looks a little different than what we typically see on agency systems, at least that I've seen. We did go through this, and if there was someone miscategorized or their abstract was really focused on a particular domain, and move them out to that particular domain. So these are really projects that are looking at kind of core and fundamental AI research without a particular application, or you might say, if that research was successful, could be applied to many different applications. Then on the right, when you look at this pie chart, is showing the breakdown of computational hours by those different fields. And so here you see a little more even distribution, as some of those domain science fields that are applying AI are larger in scale. So I thought this was actually quite interesting because it is a different breakdown than we typically see on NSF systems, and than I've seen on other agency platforms. And so I think we are reaching a different community. In terms of the DOE supported projects, there's just a couple of them here. The largest project actually is a 1 million, it's approximately a million A100 hours on Summit called Lake GPT, and it's building a foundation model for the aquatic sciences. There is a project actually for building an Earth digital twin. The PI is from NCAR. And then there is an AI project, Unified Representation Learning. This is a project that's looking at a unified representation for generative and discriminative tasks. And that's a project from the University of Maryland. I thought I would talk a little bit about some of those sort of, I would say, core or fundamental AI projects, many that are in that middle bucket category that NSF is supporting. So I'll just go through a couple of them here. There's a project from Julia Fonti at Carnegie Mellon that is investigating how to train foundation models from private federated client data. A couple of different projects. The middle one, a researcher from University of Washington, Allen Institute for AI, on how to enhance language model adaptation to be more safe and trustworthy. And then, another project, I'll highlight the one in the lower right on from a researcher at Drexel University that is looking at he described it as how models can have a sort of a prefrontal cortex to think before they output results. So a number of kind of interesting projects that are in that sort of, I would say, that core AI research space. In terms of some of the geographic diversity, it's really a key, an important thrust for the NAIR pilot to reach communities across the country. So far, the geographic impact is we're reaching researchers in about 34 different states. What's interesting is that these researchers are coming to the NAIR pilot with funding from a number of different agencies. And this really is the intention. The idea is that, there is a national infrastructure so that researchers, regardless of their funding stream, can access these resources, and that every agency is not setting up their own, mini NAIR, but there's some umbrella organization, kind of a clearinghouse for the community. I think what excites me also is that researchers, we can start to build a community of researchers across different agencies, because we know clearly that, science doesn't fall very cleanly on funding agency boundaries. Something that also is very important to NSF is seeing the different types of institutions that are supported. So many of these researchers are coming from what's referred to as R1 category research universities that provide doctoral programs. But we're starting to see a number of, smaller schools also have apply for NAIR pilot resources as well. About 20% of the awards so far have been going to minority serving institutions, and about 10% of the awards are to researchers in EPSCoR states. Let's see. We also just recently, just last month, announced the first four NAIR Classroom Awards. And again, these are resources to educators to provide resources for their students. What you can see here is these are actually 4 public universities, but they are supporting a kind of pretty varied number of students from 25 students at Southern Oregon University, a university that supports or enrolls a high percentage of students from nearby tribal reservations, to a pretty large 800 student deep learning class at North Carolina State. Now, clearly, we don't have the resources to support, every student across the country running large scale, models in their classroom. But what we're trying to do in the NAIR pilot is really understand where could the NAIR have the most impact on educators? Is there certain types of classes or institutions that really need this kind of support? Okay, I'm going to try to wrap up pretty quickly here, so there's time for questions. I might just leave you with a couple of slides and fly by the others. NSF has put out an opportunity, you can think of it as an NSF version of a FOA, to expand the NAIR pilot community. And the idea here is to broaden and diversify the workforce and the user community of NAIR pilot users here. We also have run are supporting a couple of community workshops. The first was a workshop on how the pilot can support trustworthy AI. That was this summer, and we have an upcoming workshop with jointly with DOE, which will be held at Argonne National Lab on a NAIR software stack. The NAIR task force report calls for an open source software stack. So this will be a beginning conversation. We also now have a training and events page up. This is trainings integrated from a number of different agencies, as well as non-governmental partner resources. And so that ALCF student training series is now live, I think, as of yesterday. And then finally, you'll see that we have stood up a NAIR pilot subcommittee. It's an advisory committee out of an existing NSF advisory committee. You'll recognize a number of names here. The committee has already met a couple of times, and I think are getting more familiar with the NAIR project here. It's co-chaired by Roscoe Giles, who I know is in the room, and Tilak Agarwala, who is retired from IBM. And so then in terms of our plan to evolve the pilot in the next 18 months, we still have partner contributions to integrate, and we need to mature the NAIR pilot operations. In terms of community building and outreach, we're planning to support an annual meeting in February of next year, and really continue building on the outreach and training for researchers that are new or just coming to AI. And then in terms of progress, we intend to publish a report at kind of the 1-year mark on experiences, and really focus on developing kind of the metrics and identifying gaps. So with that, I hope I have a few minutes at least to take some questions.
Sure, let's take some questions. Questions for Kate, please. Irene.
Hi, Katie. I just have a few questions about just some easy ones. So far, what's been the biggest surprise that you didn't anticipate in the pilot?
Okay. One surprise actually has been the large number of researchers that are coming from the biomedical community. And maybe I shouldn't have been surprised, but that second biggest slice is actually health researchers, and a number of them are looking for secure resources that can handle, PII. And so that is a bit of a gap. I mean, it's a pilot, so we're noticing that is a gap, but we're seeing that as really interesting, I would say. So that has been one. Maybe a positive surprise has just been how engaged all the partners have been. I'm fairly new to government, but we have an interagency steering committee, and it is well attended, and people are engaged. And I've heard that's not always the case on interagency committee, efforts. The other is that the industry partners are quite engaged as well, and so I think that's really exciting. And the model that we want to take forward is a really strong kind of public and private partnership, because I think at this stage it would be, you wouldn't be, I think, very credible to say that, you know, the government can do it all alone. I don't think it would be that credible to say industry can do this all alone. And so building a good partnership here, I think, is important.
Great. Just a two quick follow-on questions. You did a nice job. I was going to ask by scientific discipline, kind of how did the projects break down, and you did a nice job of outlining that. But a related question is, what's been the biggest barrier to access?
So I think the biggest barrier to access is the expertise and know-how to use these kind of resources. And so this is going to be, I thought you maybe asked me what the biggest challenge is. I mean, the challenge is not allocating hours, right? The challenge is engaging with communities, making sure they know how to use the resources, deeply partnering with communities that are new to AI, and making sure that's in a sustained investment and partnership. And that, you know, some people come and say, oh, it's all about, you know, the hardware. I say, it's actually a lot about the people, right? The people and the training and the expertise. And so that is, I think will continue to be the biggest challenge. You know, we don't have extra AI experts around in the country that don't have enough to do, right? People are really busy, and we need to keep training that next generation on how to use these resources.
Right. Thank you. That's very helpful. Then a related question was, either now or at the end of the pilot, what percentage of the users that are accessing these resources, the computing in particular, less so the data, what percentage do you expect to be new and never have accessed similar resources before?
That's a good question. I don't know that I have a good answer. I probably should look at see on our access systems, what is the percentage of people that come in new, and think of that as kind of a floor. And but I like that question, and I will get a better answer for it.
Thank you, Katie.
Yes.
Tina.
Yes, thank you. Quickly, I love the training that you're offering, and I see it's mostly for undergrads and graduate students, but I think postdocs and early career could benefit as well as they figure out a way to integrate AI into their research. Is there any consideration for opening it up to more people who are just new to AI?
Okay, if I gave that impression it was only for undergrads, it's absolutely not. Those trainings are open to anyone, including perhaps senior researchers that also want to begin including AI into their research. So those trainings, I mean, we're just getting them started, but they are intended to be open to the community broadly. I'll note in the NAIR classroom angle, it's not only for undergraduates, it can be for master students that are coming back for retraining. It can be for community workshops. So we're calling it kind of NAIR classroom generically, but those resources can be available for a variety of different training.
I note that Rick had something posted online. I don't know if he's still online and wants to make that question.
Yeah, I was asking and this is NAIR and HPDF, I think, share the same context here, is by avoiding the standardization of the data sets, are we not greatly limiting the opportunities for cross-disciplinary and cross-agency collaborations, as well as the ability to reuse not only the data, but reuse software that's used to ingest and visualize and process the same data?
Right. Okay. Thank you for that. I think the way I would answer is that standardization is important but it really needs to come from the particular science communities. I think a facility or an infrastructure like NAIR, and perhaps you're referencing HPDF too, can provide kind of the incentives for communities to do that, can provide platforms for people to do that. But I think we haven't seen a lot of success in infrastructure folks sort of kind of dictating or driving those standards that really need to come from kind of the different science communities.
There is a question from public, and I'm not sure, Katie, if you're gonna be able to stay until the end, but maybe we can quickly ask that question. How the outcomes of the NAIR investment in universities and classrooms is evaluated?
Right. So in the pilot, what we're looking for is for communities that are new to incorporating or bringing AI to their research. What we would like to see over the long term is, do these communities stay in the research community? Do they go on to get other federal grants? Do they become, you know, really part of the community? Now that can be hard to measure over a really short pilot, but that's what we would aim for in the full NAIR. In the pilot, we're going to be looking at usage and engagement with the resources.
Thank you. And thanks, Katie and Ben, for a great presentation. And now we should move on to our final presentation of the morning. Thank you again. So our final presentation comes from Kebak Kim, who's going to talk about building for success, I believe.
Thank you. Hi, my name is Kyoak Kim. I'm a computational mathematician in the Mathematics and Computer Science Division at Argonne National Lab. I'm very honored to be here and talk about my project, Advancing Privacy Preserving Federated Learning with Distributed Optimization, which has been funded by multiple projects, but with focus on the recent project, Express program. In the past 2 years with my collaborators, Wendy D, Ravi Madhuri, and Min-Seok Ryu, who are also the co-PI of the project, we have been working on developing algorithms and software packages for privacy-preserving federated learning and applying these to some of the interesting and important DOE applications. Next slide, please. So first, I want to introduce what federated learning is. So federated learning is sort of relatively new distributed learning paradigm that allows us to train AI and machine learning models on distributed data sources collaboratively, but without having to collect all the data into one central location. So this has, because of that particular aspect, we have many benefits, including privacy, efficiency, and scalability. In terms of privacy, since we are not, since models are trained locally, where the data is actually located, the data owners don't need to share data with the others, which is great for protecting sensitive information from the data, and for efficiency. Only models are updated. Only model parameters and updates are shared across the clients, which reduces the actually data transfer and saving storages and bandwidth. For scalability, by leveraging multiple computing resources, whether they are small edge devices or large computing facilities, federated learning techniques can scale to handle large and complex training tasks. Although federated learning is relatively new, this can be thought of as or modeled as a distributed optimization problem. In the equation on the right side, we have K clients, and each client have NK data samples. And because we have different data samples across the clients, we have different training loss function, FK. but the objective function of the optimization is the same, meaning that our goal is to find a shared or global model W that works well for all the clients. Just to explain the one of the algorithms, actually one of the simplest and most widely used algorithms in federated learning is FedAverage. In this algorithm, what we do is that clients receive the global model W from the server, and we update this global model. Model here means the model parameters of the neural net, for example. We update the model using our own local data without sharing the local data. And then our updated local parameters will be sent back to the server, and the server will receive all the local parameters and average them to update the global model parameters. These global model parameters will be shared again with the clients to proceed the training processes. Next slide, please. In federated learning, one of the benefits is that raw data stays on client devices. But we still have some data privacy issue here. Let's talk about local data retention. Although raw data never leaves the client devices, model parameters should also still be exchanged across the clients during the training processes. Because of that, without any proper safeguard, like privacy preserving schemes, model updates alone can still expose sensitive information. This actually brings us to the issue of potential data leakage. Even if the raw data isn't shared across clients or with the server, attackers with access to the model parameters can successfully reconstruct the raw data. So using differential privacy, for example, as one of the examples for privacy preserving techniques, by adding noise to the model updates, it's just one example to protect. The attackers cannot accurately reconstruct raw data from the client models or the model parameters. As you can see at the bottom of the slide, we apply different levels of privacy requirements of the differential privacy to a particular chest X-ray image data. As we increase the noise from the differential privacy, meaning stronger privacy, attackers won't be able to reconstruct the raw data from the model parameters. And I think it is also important to note that, as we saw in the previous talk, data privacy has become a national priority, as mentioned in the executive order. And particularly, it's exciting that it mentions the differential privacy guarantee in the order. Next slide, please. Privacy preserving federated learning has several applications across DOE domains. For example, in scientific experiment, we can facilitate collaborative experiments and research using multimodal data. For example, from DOE light source facilities like Argonne's APS. This allows multiple institutions to work together without sharing their experiment data, meaning preserving data privacy across the institutions, if necessary. And in climate science, research centers can securely collaborate on climate models and data, allowing them to share insights from the data, but without sharing the data. Electric grid data can also benefit from privacy preserving federated learning. We can analyze electricity consumption data patterns or train, for example, forecasting model across multiple smart devices without sharing data, which means preserving the data privacy. Next slide, please. So let's talk about the mathematical and algorithmic challenges considered in this project. So we're going to, I'm going to discuss algorithms for privacy preserving federated learning. One of the key challenges we have in terms of privacy preserving techniques is the privacy utility trade-off. Meaning that we wanna guarantee the privacy preservation without losing the model performance in the algorithm. So our approach focuses on algorithm design that carefully balance this trade-off. So for example, with this algorithm design, there are multiple different points where differential privacy noise can be injected. So we can add noise to the data directly before training, which is called input perturbation. Or we can add noise to the model after training, but before we share the model with the server, which is called output perturbation. And this is our approach, is actually basically we add noise to the training loss during the training process so we can control the noise, the trade-off between the privacy and performance. Next slide, please. In this slide, we are comparing the performance of our approach, objective perturbation, with the state-of-the-art approach, output perturbation. In the figure, our method in blue first outperforms, we can see that it outperforms the existing method in yellow. What is more exciting is that if we take, our method can be further improved by taking multiple local updates, which is in red, then and our performance becomes much better than the existing method and beyond our single update method. So that means we can achieve better performance without compromising the privacy here. Next slide, please. This is another interesting challenge we have in the federated learning, heterogeneous computing environment. So one of the issues we have is computing variance among clients, meaning clients can have different computing capabilities, which can cause significantly different local training time. Meaning, so one of the drawbacks in synchronous federated learning is that the federated learning server has to wait for all the clients before updating the global models, which can lead to significant resource waste because the faster clients have to wait for the slower clients, which is called stragglers, and which can significantly drag down the overall efficiency of the process. Next slide, please. So to address that challenge, we developed a fat compass algorithm designed for adaptively synchronizing the clients in the federated learning process. The algorithm begins by dynamically estimating each client's computing power, which allows us to adjust local tasks at the clients based on the client's computing capability. And then clients will collaborate with the server to update the global model using the client results. So in short, the idea is that if one compute machine has more computing power, it asks to run more, or it asks to work more. If one of the compute machine has less computing power, it allows to work less. So based on this algorithm, our algorithm, the right-hand side, we see the numerical results. We see that our method achieves faster training as well as higher accuracy compared to the state-of-the-art method. Next slide, please. There's another interesting challenge we tackled, which is called client drift in federated learning. Client drift can happen when clients run multiple local updates, which is very common practice to save communication. So when client drift happens, it can cause all local client models are drifted away each other and also from the global models, which reduces the overall accuracy. So existing solution techniques like FATPROP, scaffold, Fatlin, that they are very well known, can actually correct this client drift, but it comes with the following trade-off. So they have higher communication and storage cost for correction terms that they need to save at the client side, and they also have practical limitations. For example, like some can be very unstable during the training process, and most of the algorithm don't support asynchronous method, which is limiting scalability. Next slide, please. So to tackle that, we actually have developed an ARIA algorithm, which is acronym for asynchronous exact averaging, focusing on asynchronous client drift correction. So it's on the client side in this algorithm, clients save information from the previous updates rather than additional information. So we save the communication here and storage as well. And we use this information to improve the future updates. And on the server side, the federated learning server will combine these all informations to create more accurate global model. This is the very high level idea. And our algorithm, as a note, is also secure, as it is compatible with privacy-focused protocols, which ensures data remains secure during the training process. So on the right side, again, we have a figure from our numerical results. Our algorithm ARIA achieves, again, faster training and higher accuracy. So we have we can save the time, computation time as well as compared to the state-of-the-art method. Next slide, please. So let's take a look at our software, open source software package. We call it APPFL, Advanced Privacy Preserving Federated Learning. So this is APPFL version 1.0, which was just released like a month ago, meaning that we have been actively working on this software package as well. So for a brief history in one line, we actually started coding in October 2021 as a part of Palisade project. And then after 4 months, we released version 0.0.1 in February 2022. Since then, we are still actually working on that software packages to integrate more ideas and algorithms, etc. For developers, our software offers the design, simulation, and evaluation of new privacy algorithms and federated learning algorithms. For users, it supports the deployment of secure and scalable experiments across distributed computing resources. So for key features, our software can handle data and system heterogeneity that we just saw from the algorithmic side and can address privacy challenges. It is also very easy to use by simplifying the transition from the centralized training to the federated learning, and also extensible with its modular design and interface, which allows users and developers and researchers to implement new ideas and algorithms for aggregate all different type of algorithmic components in the federated learning. And our package also supports scalable deployment, and it can run across multiple HPC clusters. For example, we have been running on Polaris and on Delta as well, and we were able to run on DOE, ESNet, Fabric testbed as well for large-scale distributed experiment tests. Next slide, please. This is the table that we are comparing popular open source federated learning frameworks out there. There are a lot, including like some of the commercial ones. We are comparing many different capabilities that we can support, including how well these softwares address data heterogeneity and also support for synchronous and asynchronous federated learning, compression schemes, and versatile communication options. And we also consider features like privacy mechanisms and authentication and the possibility for real deployment, as well as other federated learning variants. So as you can see, our software package APPFL version 1.0 stands out for a comprehensive set of features. Next slide, please. And now let's look at the DO use cases of privacy preserving federated learning. So this is one use case of federated learning for load forecasting using electricity consumption data from 42 commercial buildings in California, Illinois, and New York states each. So the main challenge with this commercial building data is that the heterogeneous consumption patterns across the buildings, because we consider different types of buildings like small business, large business, schools, and hospitals, etc. So to tackle this challenge, we employed attention-based LSTM, long short-term memory, neural net architecture with personalized layers. So as you can see in the figure at the bottom, our personalized federated learning approach could achieve the lowest prediction error without privacy preserving schemes, differential privacy schemes. But if we employ differential privacy scheme, which is noted as a PPFL, privacy preserving federated learning, can successfully ensure data privacy at different privacy budget, but without losing too much about the model performance. Next slide, please. This is another use case we have with X-ray tomography data and X-ray fluorescence data, considering Argonne's APS facility. So X-ray tomography, XRT, provides detailed 3D structural imaging of materials, whereas XRF maps their elementary compositions. So these two, XRT and XRF data are complementary in the sense that XRT showing physical structures and XRF revealing chemical compositions. And they're giving us a complete view of the materials. So then in this application, why should we use federated learning? It actually can enable scalable collaborative research, as we went over briefly, across multiple experiments and multiple labs without sharing raw data. And data privacy can be maintained by keeping sensitive data local. And this can also be further improved by employing differential privacy techniques. And combining data from multiple sources can lead to better models and improved generalization. And by utilizing distributed computing powers, we can achieve resource efficiency across the multiple facilities. Next slide, please. So this is the results from the federated learning on XRT and XRF data. So by integrating distributed XRT and XRF data, we could achieve improved image reconstruction. Let's look at the figure images on the right side. We have 4 small images from XRF1, 2, 3, and XRT. So if these 4 images are the individual reconstructions without federations. So if we federated this image reconstruction with the federated learning scheme, we can achieve that federated reconstruction image on the upper left side, which is very close to the ground truth shown in the bottom left. And so from this experiment, the key takeaway is that combining these XRT and XRF data can improve reconstruction accuracy, as well as we have to develop a communication efficient algorithm for this federated reconstruction, which makes the process more scalable and accurate, even with the distributed data cases. Next slide, please. I want to conclude this presentation by taking opportunities to make some connections to our recently awarded AI for Science project. So here I have a diagram highlighting the relation across our past, current, and future projects. So our new AI for Science project will be built on the successes of my early career research project, Palisade X, and the current Express project. And these projects have already contributed to various technical areas like distributed optimization, which is very important in this context, and large-scale optimization, privacy schemes, and federated learning, heterogeneous data and heterogeneous systems, and decomposition techniques, as well as application insights as well. We are planning to explore new areas based on these research experience. We are planning to explore new areas like large AI and foundation models, incentive and fairness and federated learning, and privacy preservation at scale. And we will also build on our work in synthetic data generation, sustainable and robust workflows, and most importantly, interdisciplinary collaborations across applied math, computer science, and DOE facilities. Next slide, please. I want to take a moment to acknowledge these invaluable funding supports and research support and collaborators as well. Thank you for your time and attention.
Thank you. Let's try and take a couple of questions before we move on to the public comment. Valerie.
Thank you, Quebec. Enjoyed your presentation. Just one question, when you talk about the privacy preserving at scale, and that is looking at, is it possible to do something that's hierarchical? And that is, I know you were looking at individual sites, but it may be where there are some things like regions, you know, so for example, it may be a geographical region in which you have some privacy for whatever reason, but just was wondering if it's possible to also consider hierarchical.
Yes,
methods.
that's very good idea. Actually, we can consider geographically different regions as well. And if we look at the neural net itself, it can actually have a network structure. We can look at the different geographical region in the network, neural net network structure as well. I think that's a very good idea. Thank you.
Other questions? In that case, oh, Irene?
I'll just try one. Are you aware of any efforts? You presented a nice taxonomy of how you're evaluating the federated learning choices. And that was yours. It was a binary table. You either got a check or an X. Are there any efforts going on to come up with norms for evaluating these models on you know, across models rather than everyone inventing their own?
Right. I don't think I have the answer for that. Mainly because it's pretty new area.
I know.
The software
That's
packages
okay.
are also very new. Yeah, I think it's a good idea to come up with and think about standardized metrics for evaluating those packages and algorithms.
It would help evaluate risk, because often it's not just a binary, it's also,
That's right.
it'd be a number other than 0 or 1. Thank you.
Thank you.
Okay, thanks very much. Thank you. And thanks to all our speakers. Now we're going into sort of public comment. If there are some comments from the public, we would be very happy to take them indeed.
There was a for Ben. Let's see, I'm trying to find, yes. So there was a question from Harvey Newman. How can university-based and international groups involved in high throughput data intensive systems get involved in these great initiatives? That was mentioned in Ben's talk. One such effort of volunteers is the Global Network Advancement Group and its R&D working groups.
Yeah, happy to take that. Harvey is obviously a longtime friend and collaborator in the Oscar community. Two specific things that are happening now. The IRI leadership group in the Oscar facilities has a specific plan to get a community web presence stood up and a Slack instance, an SLACK instance stood up as the earliest platforms for virtual engagement. And so look forward to those. I want to acknowledge as well too, Harvey, and those with similar interests, that IRI and HPDF specifically start with a DOE local context and moving out from there. So they're not, there's an and both to this. We don't want these efforts, and the lab folks who are leading these efforts never want to project a sense that this is a DOE effort only for DOE. And at the same time, there are certain aspects of the effort that are very closely linked to DOE mission drivers. So, but the main message here is, yes, please reach to them and engage. there's an outreach and engagement subcommittee of the IRI group that's led by Eli Dart at ESNet and Rafael Ferreira da Silva at Oak Ridge. And so once the IRI website and Slack instance are set up, that's the front door to knock on. Two other points. I don't know that not everyone has the means or ability to make it to supercomputing in Atlanta, but at SC24, the IRI aficionados will be at the Indus networking workshop and the Workloads community BOF. I'll be there. There are probably other opportunities on the supercomputing schedule, but those are two specific ones. And of course, the DOE booth as well. There'll be a number of IRI demos at the booth. And then the last thing on my list is to note that ESNet Confab meeting in 2025 will be in the Bay Area. So Harvey, I know you're in Southern California, so not too far away. And that will have a rich IRI technical program element. So again, that's the ESNet Confab meeting. You can Google that or reach to Eli Dart and the science engagement team at ESNet for more information.
Thank you. There was a question for Katie, but I don't think that Katie is online anymore. So the question is, how can nonprofits support NAIR? We do encourage maybe a direct communication with Katie and NAIR, and NAIR and the NAIR pilot, they have well-resourced websites that might actually have some information about this question. If not, we would be happy to make the contact with Katie. So I think we have a couple of couple of minutes for more questions, if there are any more questions or comments from the public.
Okay. Thanks very much, everybody. Looks like we are done. Thank you for a great meeting and all your contributions, speakers, attendees, and virtual attendees as well, and virtual speakers. Thanks again, and we hope to see you in January.
Yes,
and
indeed.
have a safe travels back, given the weather situation that's developing as well. Thank you.